Hello and welcome to BYJU'S. Here's another video from the Target JEE Advanced series. My name is Ashish and I'm going to take you through a couple of chapters from chemistry. We're going to look at some inorganic chemistry chapters, specifically qualitative analysis, D block elements, and metallurgy. Interesting choice, right? Qualitative analysis is not really a part of the main syllabus, and it's tested a lot in the JEE Advanced. And so that's why we've chosen a mix of these three chapters. So let's see what happened in the last few years. So what we're going to do is we're going to analyze the JEE Advanced and the JEE main paper. And then we're going to do a rapid revision of all of these three things from the point of view of the JEE Advanced exam specifically. As usual, after that, we'll do some questions. Before I start, if you like this video, share it with as many friends as possible and subscribe to our channel for more such videos. Okay, so what happened in the last few years? In the JEE Advanced exam, in 2014, there was an MSQ, more than one correct answer, on copper ores metallurgy idea. Integer question on the color of sulfides. Yeah? This was a qualitative idea. This was very difficult unless you knew the qualitative thing inside out. Yeah, you tested how many of these things are black or something like that. So, pretty difficult if you didn't go through the theory in detail. 2015, two MSQs, one from reduction of iron, this was D block, and the other on blister copper, which is metallurgy. 2016 or 2015, there was another question. Group 2 cations, yeah, qualitative idea from there. 2016, an MCQ from the selective precipitation of the sulfate and another ion was there. That's again qualitative. So a lot of qualitative questions being tested with a few metallurgy and D block also interspersed in between. Copper pyrites was tested in one MSQ there in 2016, and an MSQ using sulfates, thiosulfates, and sulfides of silver. This was from D block. So mix and match of all of these different chapters we're going to look at today. 2017, just one MCQ on the displacement idea of reactivity series. This was from D block. So 2018, one MSQ on nitrates and manganese of copper. This was qualitative, and integer questions on metallurgy. So no year had all three of these chapters, which is why we've kind of combined them and we think it's good to do this in one session. And the JEE Main, however, quite different. Yeah, the JEE Main, specifically looking at the 2019 JEE, the Jan paper, there were questions on the theory aspects of D block, metallurgy, no qualitative. Yeah, so there was Hall-Herold process. Ellingham diagrams were tested. These are not in the JEE Advanced syllabus. Also, the lanthanide contraction, the whole of F block is not there at all in the JEE Advanced syllabus, but it is tested. You get one question now and then in the JEE Main exam. So yeah, and there were questions a lot. So the split wise, it was mostly metallurgy and some D block, almost equal split in the JEE Main exam. No questions on qualitative. So let's get started with a bit of a rapid revision on these three chapters right away. Qualitative analysis, very, very important idea from the point of view of the JEE Advanced exam. Now, here's the thing, you either know it or you don't. And the best way to know it is to actually perform these experiments in the lab. For some reason, if you don't have access to that, it may seem like a lot of mugging. But if you've seen these beautiful colors, the way things happen, the effervescence and all that in your lab, you'll really enjoy this part of it. And it'll be easy. Trust me, it's really easy from the point of view of the JEE Advanced exam. If you don't have a lab and you haven't experimented with these chemicals, it may be a little difficult. Anyway, let's get started with the basic radicals first. Yeah. So how do you do this? There's a flow chart to this. Yeah. And that's what you will see one by one. You start with the sample and you put some reagents on it one by one. So first you start with dilute HCl. Now this will rule out the group 1 elements that are in your syllabus, that's Ag plus and Pb2 plus. If it's a precipitate, it's a white precipitate, it could be either of these two. There are some confirmatory tests that you can revise after this. If it's a clear thing, then you go on to the next group, which is it's an acidic medium, you add H2S. Now, H2S, it dissociates, gives you some sulfides. Now, these two, copper, lead, these four actually, copper, lead, mercury, and bismuth 3 plus, copper, lead, and mercury all 2 plus, bismuth 3 plus. These will give you different colored precipitates if they are present in your sample. If they are not, it's a filtrate which you take and you go to the next group, which is group 3. Now, group 3 is interesting. You add NH4Cl and NH4OH over here to kind of reduce the concentration here, because there's a common ion effect happening here. Okay, so the concentration OH minus that you have here that would precipitate these relevant cations would be kind of lower than what you'd expect it to be. The ions here especially are aluminium, chromium, and Fe, ion 3 plus specifically, all 3 plus ions. You get a very nice gelatinous white precipitation if you have aluminium, There's a brownish precipitate if you have iron, and chromium has a green precipitate. None of these are present. Filtrate. Go to the next one. So it's a nice flowchart. It's best to do it in this order. A lot of students, what they do in the lab, teachers hate this. I just put them all together and see some if there's some color, and they're like, oh, I've got this right. But it may get you the marks in school, but if you're preparing for the JEE Advanced exam, or if you decide to do chemistry later on, life is going to be very difficult. So yeah, it's best to go through this flowchart slowly. Okay, next group, fourth group. We're going to test manganese and Zn2+. We got NH4OH and H2S. Common ion effect does not exist. Exact opposite actually. You know what happens? The concentration of H2- is higher than what it should be. The KSP value is higher. So the ideas from ionic equilibrium, when you were studying it, if you wondered where is that even useful, right here. Okay, practical aspect of ionic equilibrium. So the S2- concentration sulfide is more than what you had in group 2, and these precipitate out. MNS has this buff color. You've probably heard this if you've studied this. ZNS is white color. If there's no precipitate, you move on to the next group. Now here you have calcium and barium. The reagents are NH4Cl and NH4 ammonium carbonate. You get white precipitates from both. They're confirmatory tests. Simple idea: if you get a white precipitate, flame test. Although it's not. It's actually one of the most common tests. Yeah, calcium is a big red flame and all of that. So all the group 1 elements and some group 1 and some group 2 elements will give you the flame test, right? So that's very, very important too from the point of view of qualitative analysis. Filtrate from here goes on to the last group. The only thing that's in your syllabus here is Mg2+, and you have a lot of reagents that you put in, and if that works, then Mg2+ is present. That wraps up the ideas of cations and how you would analyze them. Remember, the main idea, the underlying idea, the theory is the common ion effect, and also the idea of KSP. So please revise that if you are looking to do this qualitative analysis. Some questions that we'll solve in the what comes after, you'll see that we've used those ideas to get to the answer pretty easily. On to the anions. What's in your syllabus is sulfate, SO42-, the halides, Cl-, Br-, I-, only these 3 halides, nitrates, and S2-. Now, although carbonate is not really in your syllabus as such, mentioned by JEE, it's a simple thing. Yeah? What you start off with, similar to what we did in the cations, you have a process of doing things. You do things one by one. You'll figure out what the anion is. The first thing that people do is add a little bit of a very, very concentrated 6 molar HNO3. If you get effervescence, CO3 exists and you're done. If no, then you go to the next step. Now here, what would remain are the other ions, which is sulfate, Cl-, Br-, I-, and nitrate. Here, I add silver, and silver nitrate specifically. You have a few drops of silver nitrate. If I get a precipitate, then you're done. You have one of the halides, white and pale yellow precipitates. You centrifuge them, add NH4OH, and you get 2 different things. You get either an ammonium complex, ammonia complex with silver, and you have white precipitate of AgCl, or you have the halogen test. There are some confirmatory tests for Br and I. So what's left now? We've removed the halogens, so we have NO3- and SO4-. Obviously, NO3- is not going to be affected by, when you add AgNO3, and SO4-, 2- also remains in the solution. They are confirmatory tests for both of these. Now, the only thing that's left is sulfide. Interestingly, sulfide is similar to what you would do from group 2 and group 1, basically of group 2 cations. You add lead, right? You get a black precipitate, PBS. So same idea here. Here we add lead acetate, and if sulfide exists, it gives you a black precipitate. This is a preliminary test. A confirmatory test of this would simply be to get sodium nitroprusside, which will give you a complex which is purple colored. Again, this is hard to remember. You have to look at stuff to tell you what it is. But if you have done this in the lab, it's going to be pretty easy for you to figure out, because of the beautiful color that you get to see. You won't forget it. It's a nice color. All right. So that kind of wraps up what happens in qualitative analysis. The only way to do this is to do this in lab. And for some reason, if you don't have access to a lab to do these experiments, then make placards, make the flowcharts, and just revise them. Yeah. And nothing's definite, but most likely you're going to get all the marks on the JEE Advanced from qualitative analysis if you just go through these flowcharts. Okay, on to D and F block elements. So much F block, mainly D block. And we'll also look at lead and tin over here, since that's in the syllabus of JEE Advanced, not so much in the main. So the thing with D block elements is that, generally they are transition elements, all this. We'll look at that. Let's do F block first, although it's not the syllabus for this, but very useful for the JEE Main Exam. Basically, these are the lanthanide series 4F and the actinide series 5F. You need to look at the whole they form F7 compounds. Generally, that idea is tested. What is the electronic configuration or color of lanthanide? Just a couple of days back on 8th of April, there was a test. There was an idea on which of these lanthanides are colored, which F block elements. So theory there, you have to go through it. Anyway, on to the ideas from the advanced. D block elements. They have multiple oxidation states, and because that all the properties are mainly because of the multiple oxidation states. Yeah, be it color, be it complex formation, and all of that. The main thing that's in this chapter is the idea of color and the oxidation states. Oxidation states are useful from the redox reaction point of view. You'll see a lot of questions from D block elements. Actually, redox reaction questions, but that could be solved knowing what happens when dichromate is in the basic medium or in the acidic medium, or MnO4- permanganate is in the basic medium, acidic medium, or neutral medium. So these reactions are very, very useful. Figure out N factors. We'll do those in the actual question parts. So revise the colors, revise the formation of these two compounds specifically, manganese compounds and chromium compounds. Besides these, there's a lot of other theory. From the JEE main point of view, there's the idea of magnetic moment. Yeah, how to calculate spin-only magnetic moment, which is fairly easy. On to the specific compounds. I've already mentioned dichromate and permanganate and the reactions. So you need to revise the reactions underlying it. This is there in standard textbooks. A lot of theory, but you'll have to read this if you want maximum marks. Yeah, if you just want to brush the surface, you make sure to get most of the questions right. Then what I've told you till now should be enough for this chapter. But if you want to get all the marks, then listen on. All right, there's silver oxides, there's silver nitrate, the formation, there's sodium thiosulfate. Generally, the thiosulfate ion, although is in the P block, they're silver thiosulfate, sorry, not sodium. So silver thiosulfate ion, the reactions and all that are very, very important from the point of view of D block elements, although thiosulfate was introduced in the P block elements. There's zinc oxide, there's zinc chloride, zinc sulfate, copper oxide, copper chloride, copper sulfate, iron sulfate, iron oxide, and iron chloride. A lot of things to do, but mostly what's tested is, interestingly, tin and lead. Yeah, specifically the compounds tin oxide, tin SnCl2, PbO, and PbCl2. The idea is that sometimes they ask you which one is most stable, SnCl2, SnCl4, or PbO, PbO2, and stuff like that. This is related to metallurgy also when you look at the extraction of PbS. We'll get to that in some time. Yeah, so that pretty much actually wraps up D block elements. I did a very quick idea. But yeah, this is one of those chapters where there's a lot of theory. You just have to read through it. If you want a quick summary, this is it. Metallurgy. Very, very vast chapter and an entire engineering branch actually, if you look at it. Anyway, we'll try and do it justice by doing a quick revision. You need to know the ores of most common elements that are present. This will help you. I know this is a little strange, this is theory, but this has come in the JEE Advanced exam and multiple times in JEE Main, but also in the JEE Advanced exam. So you got to read standard books, no other way out. And make flowcharts, make placards. I'll help you do this. For instance, what's on your screen right now. So magnesium and aluminum, they are refined by electrolytic reduction. Yeah, figure out what the cathode is, what the anode is, how the process works. There are specific names. Aluminum is called Hall-Héroult process, and there are some additives that are added to make this process easier. Need to know that from the main point of view, not so much the advanced. All right, on to carbon reduction. There's zinc, Sn, and Fe. Yeah. So tin and as well as iron, all of these have the carbon reduction idea. There are entire blast furnaces for all of these processes, and the reactions are on your screen right now. These are really important. That's why we've written our reactions specifically. These have been tested in the JEE Advanced exam as well as the main exam. On to self-reduction. Again, tested in the JEE Advanced exam. Lead and copper undergo self-reduction. Very, very important. Probably the most important idea from metallurgy that is tested time and again. Yeah, because it's very, very weird. Why does that even happen? But yeah, pretty cool too. On to silver and gold. Although silver, gold. So basically this is formation of complexes. Yeah, you form cyanide complexes and that's how these are purified along with reaction with zinc. So this is very, very quick and this is it. That's all I have for you right now. If you want a more detailed thing, you're going to have to read all the theory. But in a nutshell, this is what will help you get good marks in the JEE Advanced or even the main exam actually. For the main exam, a little bit more attention to detail from the standard textbooks. That's it from me. This question expects a numerical input as the answer. We are given that oxalate ions react with permanganate ions, MnO4-, And we're asked to find out the volume of CO2 released per mole of permanganate ions that are consumed. The deal is that there are oxidation reduction reactions that are going to happen. It's a redox reaction. The reason why we're doing this in D block is because you need to know what happens to MnO4 minus in the acidic medium, what products are formed. Yeah, that's covered in the D block elements. So we need to first form reduction and oxidation halves, balance them. From there on, it's more of a redox idea. The last idea requires you to do a little bit of gaseous state. Yeah, that at STP, 1 mole is equivalent to 22.4 liters. So let's get started with the redox reactions. Yeah, the oxidation half is going to be oxalate ion, C2O4 2 minus, giving you CO2. Now, what's the change in oxidation number that's happening over here? Oxidation number of carbon here is +3, and this becomes +4. This is a direct idea. Yeah, I'm just doing that 2C plus -8, which is 4 oxygens, is equal to -2. So this goes the other side, and C is equal to +3. This is on the LHS, yeah, the oxidation state of carbon there. RHS is simple, yeah, it's +4. Now, here's the deal. There are 2 carbon atoms, okay, on the left-hand side, and just 1 there. So the actual changes of 2 electrons. So this is +3, +4, and 2 electrons on this side. Yeah. This is basic balancing idea that we can do over here. So this seems okay. Everything is balanced. The number of atoms, the charges, yeah, everything seems to be balanced in the oxidation half. Look at the reduction half. MnO4 minus becomes Mn2 plus. This is the D block idea that you need to know to even start this, okay? This is going from 7 plus to 2 plus over here. This accepts 5 electrons over here. This is a standard thing. If you've practiced even a little bit of D block elements, you'll know this. So this is a direct idea. From here on, but it's not completely balanced. Let's first balance it. Yeah, I need to add, what do? I add 4H2 over here, right? To account for the oxygen atoms that are not balanced on the RHS. And yeah, I also need to add how many do I have? I have 8H plus on the left-hand side. Now, is everything balanced? The charge, there's 2 plus on the right-hand side. That's over here. What's the total over here? That's -1, -6, and +8. Yeah, 2 plus here, 2 on this side. So charges are balanced. H atoms are balanced, oxygen atoms are balanced, and so is the manganese. So yeah, this is completely balanced. The halves are completely balanced, but to do this completely, the total number of electrons exchanged must be the same. So we take the LCM, same old stuff, multiply this reaction with 5, this reaction with 2, add them up. The reason I'm doing this is you need to know how many moles of carbon dioxide are formed per mole of MnO4 minus consumed. Then we convert that using the idea of 22.4 liters is equal to 1 mole. Yeah, if it's a gas, CO2 is a gas. We need to find the volume of the gas release, right? That's why we're doing this. Yeah. From here on, go ahead and balance it. This is the balanced equation. I've just added things together, put in the numbers. And yeah, from here you get to know clearly that for say 2 moles of MnO4 minus, which is your permanganate ion, you get 10 moles of CO2. So per mole, you have 5 mole of CO2 produced, and multiply this with 22.4 liter per mole of CO2 again, to get the volume, which is equal to 112 liters, which is your answer. So a direct question, just by a couple of steps, and also what happens to the permanganate ion in the acidic medium. It goes from +7 to +2. Oxalate, yeah, that's a little tricky if you haven't seen it before. Yeah, you may, if you haven't practiced this sort of question in redox reactions, this may seem difficult, but otherwise it's a fairly direct question. You just need to add a little bit of gaseous state ideas. Answer is 112 liters. Okay, here's a question that requires a numerical input as the answer. This is a question from Metallurgy. There's a process that's happening here. It purifies galena. We need to find the weight of lead in kilograms per kilogram of oxygen consumed. And there are 1,000 kilograms here, yeah, given to you. So what's your approach going to be? Well, first, we just need to read the process. Yeah? Figure out what the reactions are going to be. We need to write those reactions down. And then balance the equations and get the mass of PV. It's a simple idea, but you need to know what's happening. Yeah? There's some ideas of self-reduction and partial oxidation. So let's see what happens. So first, the first reaction over here shows you the partial oxidation of PBS. Yeah, let me just write that down for you. This is partial oxidation. So this is an unbalanced reaction. Yeah? PBS reacts with oxygen, gives you PBO plus SO2. Clearly unbalanced, right? So how do I balance this? Let me put a 2 behind this because there's an odd number here, an even number here. So that's 2 PbO, 2 SO2. Okay, then there's 2 here. Okay, then I put a 2 here. Okay, now I've got too many oxygens on the right hand side. 3 here. Yeah, this seems balanced. I have 2 leads, 2 sulfurs, 6 oxygen atoms. Yeah, this one's balanced. The next one is the self-reduction process. Yeah, so I cut off the supply of air, but I still keep the heating going. So I have PbO and some PbS, yeah, the galena thing. So there's self-reduction happening. And the product that was formed, that itself oxidizes PbS, galena. And this is what happens here. You get Pb plus SO2. Yeah, a standard reaction that you must know if you've gone through the metallurgy ideas for lead. Okay, so what happens over here? Let me just give you some space. Okay, balancing wise, I think I'm going to have to put there's SO2 here, S here. Okay, let's put a 2 here to balance the oxygens first. And now I have too many leads, so 3 leads specifically. I think that's it, right? I have 3 leads, I have 2 oxygens, I have 1 sulfur. Yeah, this one's balanced as well. And then I just add them both up. And guess what? These guys go away. This gets cancelled out when I add them both. What else? Is there anything else that gets cancelled out? No. This gets added to this. And oxygen comes here. This also gets added to this. So the reaction that I get in the end is this one over here. Yeah. 3 PbS plus, is that it? Yeah. 2 from here, 1 from here, plus 3 O2, all 3 from here. Give me 3 Pb, which is all from here. 3 SO2, which is this plus this. So this is my balanced reaction for this process. Balanced and also added up both the things that are happening. So yeah, we need to find out the moles of oxygen consumed. The mole of oxygen consumed is going to be same as the mole of Pb formed. Yeah, look at this. Just go back up there again. Yeah, so there's 3 PbS plus 3 O2, right? So equivalent number of moles here both. Which you can cancel all the 3's out. The same thing. So the mole of oxygen is simply going to be how much? So you have 1000 kg of oxygen given to you, and the molar mass of oxygen is 32 grams per mole. That's what's written over here. Yeah? So whatever this value may be, we don't really have to do this calculation. Let's just keep it as it is. The weight of lead is simply going to be whatever this number of moles is, multiply that by the mass of lead, the molar mass of lead, which is 207 grams per mole, which is what I've done over here. Just a bit of cancellation. You divide this by 8, you get 4 here, you get 125. And on a bit of math, you get this to be 6.47 kilograms. Okay, that's it. The reason why I've kept the units as I've left it as kilogram. Usually what I do is I convert to grams and all that. Is because you require the final answer in kilograms. Yeah, and here, as you can see, this gram unit gets cancelled out, mole gets cancelled out, and what's left is just a kilogram unit. Yeah, that's why I left that there. Usually I say you must always convert to units. That's fine and good, but this question expects the answer in kilogram, which is why I let it be there. All right, answer 6.47 kilogram. Quickly recap of what we did. Read the question out. Wrote down the relevant reactions. Yeah, first is the partial oxidation. Why partial oxidation? Let's just go back there. Why partial oxidation? Well, this is the reaction here, right? Pb can form PbO2, which is complete oxidation. Yeah, and here we are only going half the way there, so it's PbO. And then we stop the supply of air, heat it a lot more at a higher temperature, and then you react it, which is basically reacts with galena and gives you this product here. We add them both up, and then we do this math and get the answer to be 6.47 kilogram. Really interesting question here. And this is from D block and uses the ideas of redox reactions. MnCl2 is dissolved and in KMnO4. This then reacts with 225 milligrams of H2C2O4. I've kind of condensed the question. It says a lot more things, but that's the crux of it. That's what's really happening behind the scenes. What's the approach going to be? Well, simple idea, just the one-step idea is that the number of equivalents reacting will be the same. Okay, that's the most important idea over here. Irrespective of what reaction happens, the number of equivalents are going to be the same. So what we'll do is we'll find out the equivalents of in one step, and once we get that, in all steps the number of equivalents will be the same, and we'll use that to get the mass of MnCl2. But for that, the first thing is what happens to oxalate? How do I find the equivalent mass of oxalate? I know the total mass is 225 milligrams, right? That's given to me, that reacts finally. But what's the equivalent mass of oxalate going to be? How much that's going to react with KMnO4? So oxalic acid or oxalate ion, as I've written over here, this is C2O42 minus, giving you 2 CO2 and 2 electrons. I've just kind of short circuited this. Basically, this changes from +3 to 4+, And since there are two of atoms here of carbon on the left hand side, you get 2 electrons over here. So the N factor of this is going to be 2, which means that whatever the molar mass of oxalic acid is, you divide that by 2 to get the equivalent mass. That's it. And from that, we can get the number of equivalents of oxalic acid that were provided to us, that reacted with the KMnO4 that was formed from the first reaction. Okay? All right, let's see. So what's the equivalent mass of H2C2O4? The molar mass is, I've done the calculation here. So basically there's 2 hydrogen atoms, 2 carbon, and 4 into 16, which is 4O. Yeah, this is not 40. Let me just write that down properly. This is 4 oxygen atoms. Yeah, looks like 40 now that I see it. Okay, there's 4 oxygen atoms, 2 carbon, and 2 H. And so that divide the whole thing by 2, which you get 90 by 2. And this is the equivalent mass, 45 grams. From here, you can find the number of equivalents of the H2C2O4 that reacted in the end. Yeah, kind of backtracking, but that's fine. It's fine. Okay, so number of equivalents is simply what? It's going to be 225, which was given to us, milligrams, divided by 45 grams, which means that this 5 milli equivalents. I've just kept this milli guy. I've cancelled all the grams. I've kept milli around. So yeah, that's it. So this 5 milli equivalents. That's it. That means that 5 equivalents of all the reactants and products are that's the amount that is going to react. But what happens to KMnO4? Yeah, how did KMnO4 form in the first place? Let's see. To get the mass of MnCl2, remember MnCl2 is manganese in its +2 state. In the acidic medium, what happens? It goes from Mn2 plus to Mn7 plus. Yeah, so this is Mn2 plus giving you MnO4 minus, which is basically 7 plus, which was KMnO4 that reacted with the oxalate, yeah? The 225 grams. Let me just write that down. That's what's happening there. Oh, milligram, not gram. Oxalate. Got erased. Okay. All right. Just to give you a clear picture of the big picture of what we're doing. So the mass of MnCl2 is simply going to be number of milli equivalents times the equivalent mass. This will give me the mass in milligrams, yeah, if I do this. So I'm doing the same exercise again, finding out the mass, dividing it by the N factor, which happens to be 5 because of this idea here. Yeah. Remember, oxygen state is changing from +2 to +7. And that's it. That's it. Whatever this gets. So this 5 basically just cancelled out. Yeah? So whatever the mass of MnCl2 is, just going to be 1 mole of this. How much is that? It is 55 plus 71. It's 126 grams. Answer. That's it. So, seems a little convoluted, but the basic idea was very simple. Let me go over that entirely quickly. The number of milli equivalents is going to be the same. I have the final mass that reacted, yeah, of oxalate, which was 225 milligrams. But how did it get there? How does oxalate react with MnO4 minus? So oxalate becomes CO2, and that the change there is going to be of 2 electrons there, right? So that's why the mass, the equivalent mass of that was 90, the molar mass divided by 2. And then we got the number of equivalents, which is 5 milli equivalents, okay? Wait, hold on. So this is not 126 grams. It's going to be 126 milligrams, right? Let me just write that down. Okay. If we start with 225 milligram, let me check. Is that what was it 225 milligram or gram? Okay, yeah, it was 225 milligrams. So we got milli equivalent, which means that this is going to be milligrams and not grams. That's the answer, 126 milligrams. And yeah, once we got that, we got the number of equivalents to be 5 milli equivalents. That's what's going to react. I just multiply that with the equivalent mass of MnCl2, which happens to be the mass. So this is one place where students could go wrong. You would just divide by 2 because look, the charge on this is +2. So you're like, hey, you know what? The N factor is going to be 2. But this is a redox reaction. Be careful. Yeah, it changed from +2 to +7, which is why N factor here is 5. And this is one place where you could go wrong. A lot of students do go wrong here. We won't do that mistake. All right. Answer here is 126 milligrams. This question can have more than one correct answer, and this is based on the idea of qualitative analysis. So let's see what needs to be done. We need to differentiate between the salts of the nitrates basically of Mn2 plus and CO2 plus. We need to figure out the correct option. So let's look at them one by one. There's also some oxidation the reduction potential values idea also there. Let's see. First one says that Mn2 plus burns in a characteristic green flame. Only Mn2 plus. But this is not true. Yeah, if you've gone through the theory, you'll know that both Cr2 plus and Mn2 plus, both of them burn with green flames. So this one's not right. We need to select the correct options. Let's look at the next option. Here, what happens when you pass H2S in acidic medium? Yeah, copper precipitates out, that's fine. It's in the earlier groups, right? When you look at the cation qualitative analysis, sure. But Mn2 plus, does that precipitate out or not in acidic medium? Well, the KSP value of Mn2 plus when it reacts with H2S is higher, which means that it needs a higher concentration of H2 minus than it would get just from the dissociation of H2S, which is why we add H2S as well as NH4H, which means this is in the basic medium. Yeah, these are the reagents for to precipitate out Mn2 plus. So what does this do? How does this increase the concentration of H2 minus? You see, the first reaction, this forms H plus ions. The second reaction in the basic medium forms OH minus ions. Both of these react and form water. This is why, so if this gets consumed and this gets consumed, that means that both of these reactions, this gets pushed in the forward reaction, this also gets pushed in the forward reaction, which means this concentration H2 minus increases, reaching that higher KSP required for Mn2 plus. Long story short, yeah, this one's correct. In an acidic medium, Mn2 plus will not precipitate. Also because if I add H plus, that's a common ion, and then this pushes this reaction backwards. Yeah, which reaction? This reaction specifically. It's getting crowded. But you get what I'm saying. If I add H plus over here, then S2 minus concentration will decrease. Yeah, so not good for Mn2 plus precipitation. So this one's correct. So only copper 2 plus precipitate out when H2S is passed in an acidic medium. This one's correct. Let's look at option C. Okay, I've drawn a bit of a graph for you here because that's the only way to remember this. This is completely theoretical, this part. It says that E naught of CO2 plus versus Mn2 plus when they get converted to Mn and CO. Basically, M2 plus to M. That trend. If you have gone through a standard textbook, you'll know right away that there's a dip in the graph, yeah. And if you've paid attention to where that dip is, it happens to be on manganese. After that, this still increases. The ones that come, after this, elements that come after iron, still keeps increasing. So the dip, if you just gone through the standard textbooks for the exam, you'll know for sure that manganese has a dip. And if you look carefully, then this is a more negative value, yeah, which means that the absolute value is larger, but it's more negative, which means the copper value is higher. Copper happens to be much over here, yeah, somewhere over here in this thing. Oh, this is copper, chromium. Wait, what are we looking at? Oh yeah, copper. Cool. This is good. Okay. So, this one is correct. Yeah, that is the E naught of CO2 plus is higher than that of Mn2 plus in E naught reduction values. And that's it. I think we've gone through all the 4 options, right? So the correct options are options B and D. Let's look at what we did quickly. Let's revise. Let's go through all the options again. First option was said that Mn2 plus has a characteristic green flame. Both of them have it, so this one's not correct. Next option talks about passing H2S in acidic medium. Does not work. In the basic medium, however, it does, as I explained to you. So, which is why B is correct, C is not correct, and D, which is, it talks about the E naught reduction values, that's correct because of this trend that I just showed to you. Answer the option B and D. Here's a question that requires a numerical input as the answer. Now, very, very interesting question. We're given that 1 mole of KMnO4 reacts separately with some compounds. We have to find the total number of moles of the compounds that react with 1 mole each of KMnO4. What's the approach going to be? Redox reaction idea, but requires you to know what products will be formed. There's some Fe and Mn. So what happens? That's a D block idea you need to know. So for all the reacting species, as usual, the number of equivalents is going to be the same. So I need to just find out the number of equivalents that are there, 1 mole of KMnO4. Okay, KMnO4 is in its acidic medium, so that means that Mn7 plus goes to Mn2 plus. This is getting reduced, which means that this is an oxidizing agent. Now, that is a key idea here. You need to look at the species, see which ones are being oxidized, how they oxidize, and take it from there. From that, you're going to get the N factor of all these species. So clearly, the this 1 mole of KMnO4 has 5 equivalents. We'll use that idea. And then when we get the N factor of all the other species, use this to get the number of moles of the species. That's it. Sounds really simple. A little tedious because you have a lot of compounds. You need to figure out what happens. That's what we're here for. Let's do this. Okay, first compound, FeC2O4. Oxalate ion of Fe. And you can see that both of them have a 2 minus charge. I mean, Fe2 plus and C2O4 2 minus. So, which is why I've written this down. So, Fe2 plus becomes Fe3 plus, C2O4 2 minus becomes CO2. Am I sure about this? This is oxidation. Let's see. This is plus 2, 2 plus 3. This is plus 3, 2 plus 4. Yeah, both of these are oxidation. And since there are 2 over here, let me put this up. So, this is 2 electrons here on the side. Does that make sense? Yeah. Plus 1 electron on the side. So, the total N factor for this compound in its entirety is going to be 3. Be careful about this. You need to add them both up. Yeah, both these species being oxidized. And that's the trick in this question. With maybe other compounds also, you may see that, but this one's happening for sure. We'll see what happens in the next compounds. So anyway, so there's 3 equivalents per mole. That's what the N factor means, right? Use that idea. So 1 mole of KMnO4 had 5 equivalents. 1 mole of FeC2O4 has 3 equivalents. So how many moles of FeC2O4 will have 5 equivalents? That's what you need to find. Yeah, because it's reacting entirety with 1 mole of KMnO4. Okay, so that's simply going to be 5 by 3. Simple unitary method here. 5 by 3 moles. That's for this guy right here. Let's see the next compound. Yeah, you have FeC2O4 whole thrice. Interesting. Wow. Wait. The previous compound also had iron and oxalate ion. What changed here? Fe3 plus is involved here. Yeah, it's in its max oxidation state. No more oxidation happening. Don't write Fe3 plus gives Fe2 plus. Don't do that. That's not going to happen. This is an oxidation reaction. When Fe3 plus, when this compound reacts with KMnO4, it's not going to get reduced. It's only going to get oxidized. Yeah, so please be careful about that. So the N factor here is only going to be because of C2O4 2 minus. As usual, I'm going to have to put a 2 on this side here. This is plus 3, 2 plus 4. We just do the exercise. Here's the thing. Each mole of this compound has 3 moles of the oxalate ion, C2O4 2 minus, right? So per mole, if the change is 2 electrons, so there's a total of 6 equivalents per mole. Yeah, this is a per here, this is like backslash. Let me just write that properly. This is per mole, right? So be careful about this. Yeah, 2 things here. One thing is that Fe3 plus is in its maximum oxidation state, so nothing's going to happen there. Oxalate sure gets oxidized, but there are 3 moles of oxalate ions per mole, change of 2 electrons of 2 oxidation state. So the 6 equivalents per mole. And we'll do the same exercise again. Yeah, 1 mole of KMnO4, 5 equivalents. 1 mole of this species here, Fe whole twice C2O4 whole thrice. Yeah, be careful about the formula there. How many moles are going to get formed over here? How many moles would react with 5 equivalents? It would be 5 by 6 moles. Slightly smaller, a little less than 1 mole here. Okay, getting somewhere. Just a couple of more compounds to go. FeSO4. That's the next compound. Only thing that's happening here is Fe2 plus becomes Fe3 plus. Yeah. S it is in its maximum state, which is plus 6. It would be really complicated if there was something else here, but luckily for us, it's not. This Fe2 plus to Fe3 plus, and this is plus 2 to plus 3, which means that it's just, 1 equivalent per mole, right? Simple idea here in factors 1. Same exercise repeated. 1 mole KMnO4 gives 5 equivalents. 1 mole here of this compound is 1 equivalent. So how many is 5? It's simply 5 moles. Last. Let's see what have we done. How much do we have still now? We have 5 by 3 for the first one, 5 by 6 for the second one, and 5 for the third one. This is what we have so far. Just doing a bit of just keeping things together. This is what we have so far. Last compound. Fe2SO4 whole thrice. Now, this is examiners playing a bit of a trick on me. Fe is already in its maximum state. It's 3 plus. SO4 also, S is in its maximum state. So nothing happens here. There's no reaction because look, for the reaction to happen, what was happening? Yeah, you had the manganese, right? So that was getting reduced, right? Mn2 plus. Mn7 plus had to become Mn2 plus. And that would only happen if there was something to oxidize. Since there's nothing to oxidize, reaction. So the last compound does not react, which means that our answer is just going to be the sum of the previous things, which was, how much was that? It was 5 by 3 for the first one, plus 5 by 6 plus 5. How much is this? Let's take LCM and all of that. LCM is 6, right? So I put a 2 over here. 2 into 5 plus 5 plus how much is this? This is 30, right? 6 into 5 divided by 6. This is 10, 15 and 30, 45 by 6. This is 7.5, which is your answer right here. Now the approach in itself was, I think, straightforward. Just a little bit of, you had to be careful in knowing that it's Mn 7 plus, that becomes Mn 2 plus. And let's just go over that again, right from the beginning. Yeah, let's go to the approach. Okay, now for all the reactant species, the number of equivalents had to be the same. How many was that? 1 mole of KMnO for the reactant, which means Mn7 plus becomes Mn2 plus, oxidizes those species, which means the species should be capable of being oxidized. That goes without saying. That was the one trick, two things that you had to keep in mind. A little bit of a complicated question, but yeah, it gives you immense joy to get it right. Answer is 7.5.
For more videos and live lectures on the JEE, click on the subscribe button now.